We are on the last part of the course. Of course, I wanted to do something more, but the timing, of course, is very less. It's not possible to cover a vast thing like this in just a matter of 3 months. So, in this section, we are going to focus on the convex programming problem. Convex programming problem means either you're maximizing over in a concave function over concave inequality, an affine equality constraints, and an abstract constant given in terms of a inclusion to a convex set, or you are minimizing a convex function with convex inequality constraints and affine equality constraint. Please understand, when you are talking about equality constraints, whether you are talking about concave maximization or convex minimization, you have to understand that equality constraints always has to be affine in a sense, because if you take a non-affine inequality constant, that is, you take a non-affine convex function. For example, I take set of all xy in a two-dimensional plane such that x square plus y square equal to 1. So it denotes the circle centered at the origin of radius 1, but it only talks about the circular boundary. It doesn't talk about any point inside. So this was on the circular boundary. If you look at it, just the circular boundary itself is not a convex set. So affine function, a non-affine convex function being equated to 0, all the x's which satisfy that need not form a convex set. But for affine function, it necessarily does. And I am sure that you can easily prove it, so I'll not go to do that. Though I would like to cover the affine functions here, it's not a very big issue. But because of the time, I wouldn't be able to complete, because this is the last part one lecture. And what I'm planning to do is that in future I'll put up the notes somewhere. And what I'm planning to do is to consider a much more simpler problem to this problem CP, the convex programming problem. So here I'm going to go in my favorite approach, the minimization approach. We'll also talk about the maximization approach at the end and write down the result in a way economists would like to prefer. So because though I'm an optimizer, a classical one, I guess, but I still keep in mind that these lecture notes are written for students in economics or even for some possibly young economic researchers. So what happens is that we will look into this problem CP1, which will consist only of inequality constraints and the abstract constant, and these equality constraints would be forgotten for the time being. Now, if I say F to be the feasible set, that is the set of all x such that gix is less than or equal to 0 and x is element of x, then our problem is to minimize fx over f. Now, how do I now get an optimality condition? Most people, those who have some idea of optimization, would know that we are leading towards the famous Karush-Kuntakar conditions or KKT conditions. But it is extremely important and important to note here that there are several different approaches by which you can reach the Karush-Kuntakar conditions. But for logical consistency of the approach that we have taken towards optimality condition, by advertising the normal cone as the main vehicle of generating optimality conditions, if we take a different path, which we can easily take, which we will take when I form this as a real book chapter, I'll actually I'll show you those different paths. But those different paths are not shown in this particular course. It's not required. Here, the advertised goal of using normal cones would play the central role. So, which means that if I have this set F, which is a feasible set, for this set F, how do I write the normal cone? Of course, the necessary and sufficient optimality condition in this case is that any x which satisfies this inequality or this inclusion would not inequality, sorry, inclusion would actually satisfy the would actually be the global minimizer. Of course, you can write f as f1 intersection x, where f1 itself is this. So if I can write the normal cone, if I can compute the normal cone of this, then I can obviously compute the normal cone of f1 intersection x, right? So our goal in this talk would be to have an outline of how to compute the normal cone of this. So a normal cone, because I have the set given f1 where the set of all x satisfies this is set of all x's satisfy x gi x less than equal to 0, which are m inequalities where gi's are convex functions. Our aim, as I told you, is to compute this normal cone to f1 at some x where x is in f1. So we are logically on track because again we are trying to now compute the normal cone. So the computation of the normal cone is the key idea. Now you will later on see that the Karush-Kuntakar multipliers or some kind of Lagrange multipliers, or this Lagrange multiplier term you have heard even when you did calculus, this will turn out to be the, the key elements, the keys vector which actually would generate the normal cone. So the approach of making normal cone the main vehicle to deliver optimality condition brings in a new interpretation of the Lagrange multipliers as a geometric object. It is trying to construct a kind of cone. It is trying to construct the normal cone. So these are key elements which computes the normal vector such that negative of the gradient should exactly match that vector. So when I want to compute the normal cone, I should be able to do it with respect to the data. Here I know that the functions are differentiable. So given a gi, I will also know about gradient of gi at any given point x. So it's very important for me to know the normal cone to f1 at x in terms of the data. So how do I visualize what is the normal? How do I start even thinking about how to compute it? To compute the normal cone. If you just give it to me, it looks I'm completely lost. But you are not really lost. If you look at a feasible set, what does it means? So here you will have a surface given by gix equal to 0, say in 3 dimension. Because any 3 dimension the surface is given, say n is R3. So you will have gxyz less than equal to 0. So it will be a surface because gxyz equal to 0 is a surface. Less than equal to 0 means everything below it, below the surface. So if you want to compute the gradient, so now you are looking at a point at which you want to compute the gradient. Basically you want to compute some kind of a normal at a point which lies on all the surfaces. So it's in the intersection of not all the surfaces but several surfaces. So F1 is a body which has a surface whose surfaces are made up of parts of the surfaces created by the functions gix equal to 0. So if you know of any three-dimensional function phi x y z equal to 0, then the gradient of this phi at at a point x y z is perpendicular to the surface x y z at R. So here by a normal cone, we know that x bar must be in the boundary. So boundary means it either lies on a surface, only one of the elements it lies on a surface, or it lies on the intersection of several surfaces. So basically, x bar is such that it satisfies with equality some constant gix bar equal to 0 and some with strict inequality. So that's the idea. For something it is on the surface and some things it is not on the surface. So for those it is on the surface, those gix equal to 0, the hypersurface that they create, because here we are not talking just in 3 dimensions. So the hypersurface that they create, gix gix equal to 0. So either the point is, suppose point is on the boundary of, so there are 3 and the point is on the boundary of the intersection of 2 surfaces. So g1, suppose g1 and g2 are those 2 surfaces, then g1 x bar equal to 0 and g2 x bar equal to 0 because they are on the boundary, while g3 x bar must be strictly less than 0. So So x bar is such that some of the GIs are satisfied with equalities and some of the GIs are not satisfied with inequalities. And this brings us to a crucial notion called the active index set of a at a given point x bar. So the active index means we are looking at which surfaces or the function x bar, the point x bar lies. So basically find out all those indices I for which gi x bar equal to 0. So these are the, so if I want to compute a kind of normal, this is, and the gradient actually is the normal. So this is the surfaces, these are the surfaces that I want to consider. This is the surface that I really want to consider. So this active index sets are the indices. Those are the constants which I'll be considered, because in at that point where the if x bar is in the intersection of all those, at that point I can actually construct a normal because they're on the surface. So that's, and you know the gradient itself is in the normal. So if I is in ix bar, then is gradient of gi x bar is a normal vector to f1 at x bar? That is a very simple question to ask, because that is what it should be, because the greater grad of gi is actually normal to the surface gi x equal to 0. The convexity gives us the answer, because this is what it means. For any I element of ix bar, this is what will happen. So this is for, of course, you take any x is, this is true for any x in R, and now gi x bar equal to 0, and if I take x element of this set f1, then what would happen? Then this would be also gix would be less than equal to 0. So gi x bar x minus x bar is less than equal to 0, which means for any x in f1 this will be true for any I which belongs to the active index set I of x bar. So gradient of gi x bar is element of nc x bar for any I. But because it is a convex cone, I can make this kind of combination with all the grad GIs where I varies over Ix bar, and such a stuff, such a combination must lie in the normal cone. Of course, because if grad GI lies there, lambda I any for any grade lambda greater than 0 also is in NCX bar. Because it is a convex cone, I can simply add the elements vectorically and all of them would remain in the convex cone. That is what it means. So now consider a set. So maybe we are getting a hint as to what the normal cone might look like. So it's a hint. This is how mathematicians start getting a hint that this is possibly the structure. There is, of course, no way to know before and unless you prove that, okay, what you are inkling at is true. But you know, large part of scientific thinking or mathematical thinking rests in our imagination. So we have to imagine something nice and try to see whether that works out. If that works out, it is good. If that doesn't work out, very sad. Nothing can be done. So let us construct this set S of x bar, which consists of all elements of this form, where lambda is greater than 0 and I is varying over ix bar. Of course, if you change your x here, then this ix bar changes, right? So what we have just shown that S of x bar, so if you take any element of this form, that will actually belong to the normal cone. Here, sorry, I made a mistake here. I am making a mistake here. This cannot be C. This is F1. Grad GIX is element of the normal cone to F1 at x bar, because x is in F1. Here also it should be F1. Here it should also be F1. Sorry for the mistake. So in the typed version, everything will be corrected. And so this shows that this element actually belongs to this whole set is a subset of NF1 x bar. Our question is that it would be a good idea if I have Sx bar itself to be the normal cone. Then it makes much more sense, because then I can express optimality condition in terms of the gradient of the known data, because that's what it will give me. So immediately you know what to do. If you can actually show that the normal cone is this under some condition, then what I will get is this. I'll simply write, suppose this was f1, there was no x here, or x was open. If this was f1, this so I will have some lambdas i's for which summation lambda I grad g I x bar, where I varies over I x bar, is an element of nfx bar whose sum with grad fx bar would give me 0, or minus grad fx bar can be exactly written in that form because it's the element of nfx bar. So f1 x bar, so it can be written in that form in terms of the gradient of gi's. So in terms of some positive linear combinations of the gradient of gi's, those lambda i's that you see here, we will call them Lagrange multipliers or Karush-Kuntaka multipliers, which I do not mention because that will take us into too much detail. But that's just for the interest I'm telling you. These will be called Lagrange multipliers. So these Lagrange multipliers are actually a kind, what they're doing, they are generating this set which will finally be equal to the normal cone under certain condition. And let us see what is that condition under which such a thing would happen. We will first show that Sx bar, this set, is actually a convex cone. So the fact that Sx bar is a cone is so simple that I wouldn't even dare to prove it here. To prove that Sx bar is a convex cone is to just to take two elements, say V lambda and W mu in Sx bar, and then add them and show that it again lies in Sx bar, because V lambda here denotes the generating multipliers. So V lambda is written by summation lambda I grad gi x bar. Grad gi x bar is fixed. So the generation is done by this lambda is. So grad gi x's would be actually formally called generator, but without changing the lambda i's, new elements won't be generated. So V lambda and W mu. So these are two vectors, both of them lying in Sx bar. Suppose you add them up, phi lambda plus W mu. If you add them up, what are you going to get? You are going to get a thing like this. But lambda I plus mu I, both are non-negative. If you join them up, they will be non-negative if you add them up. So V lambda plus mu lambda is also an element of Sx bar, showing that it is a convex cone. So these type of cones are typically called finitely generated cones, because this gradient of gi x bar, where and I is in I x bar, so the finite number of I grad j x bar only naturally. And these are called generators of the cone, generators of the cone Sx bar, which will be actually the normal cone. So in general, a cone V is called finitely generated if there are certain fixed k vectors, say 1 into a k could be anything, such that any vector can be written as lambda I equal to 1 to k, lambda is greater than equal to 0. It's a tricky thing to prove that it is closed, and proving that it is closure is also a key thing to prove the Farkas lemma, which is an important idea, but we do not have those time to discuss such things because we had been discussing a lot of other things since then. But here, this is a very interesting fact, but we won't be able to do it. That this kind of cone is called a polyhedral cone, because if you draw a finitely generated cone, you will see that it is intersection of polyhedral half. It is intersection of half spaces, but those half spaces are formed by hyperplanes passing through 0, through the origin. That's the key idea. So in this particular setting, A1, A2, AK are called the generators of the cone. So a key fact about a finitely generated cone is that it is closed. I was looking for a proof, and then I am always surprised by the Russian approach to things, and you may not be finding a very satisfactory simple proof in many books, standard books, but suddenly you will find one Russian book written way back, a beautiful simple proof is given. So I have a collection of several of these optimization books, Russian books. There was something called the Monisha bookstore, Monisha Granthala in Calcutta, where I used to often visit as a young student, and I used to pick up books very cheap, 10 rupees, 20 rupees. So this book by Karmanov was also picked up at very 10 rupees or 20, 15 rupees, I do not know. It was published by Mir Publishers Moscow, who used to translate the works of Russian mathematicians into English and then published them. So you can see it's way back in 1989 actually. I had I just picked it up by looking at it, found it pretty little interesting, just read through it and just got it. I wasn't, I had not even completed my graduation when this book came. Possibly I had my BSc. Possibly I've picked it up when I was in just in the masters or just closing up, only just finishing masters. So there he proves that a finitely generated cone is closed. The idea is to use mathematical induction. So if you take just one vector ai, then lambda I ai, where lambda is positive, so a1 say, so lambda 1 a1, where lambda 1 is positive, this, as you vary the lambda 1, which is greater than equal to 0, you actually look at a ray emanating from 0 and moving along the direction of a1, which means it is just a half line, and half line is a closed set, which you know. Now you use induction. So you will say, okay, if I have k generators, then suppose I know that a1 to ak minus 1, if I take the k minus 1 generators, then I will be, the cone that is generated, the finitely generated cone would be closed. Now if I add one more generator, then the new cone, that should also be closed. In that way you can move gradually from 1 and come up to m and show that this Vm is closed. This Vm is written only to say that there are m generators of this cone. So I will not get into the details of the proof because it will take us away from what we are trying to do in this section, rather outline a proof of how to compute the normal cone in essentially showing that under a very mild assumption called the Slater condition, the normal cone to n f1 at x bar is exactly equal to sx bar. So this is a key idea that you have to keep in mind, that that's what our aim is. So here, some people can read the proof. It's not possible to discuss all of these now because as the course is ending, and you know we always hurry at the end of the course. But anybody who wants any discussion with me, and obviously write an email to me and discuss it, and the course notes would anyway be available. So what does it say? It says that if the Slater condition holds that there exists a x hat in Rn such that gi x hat is strictly less than 0 for all I, not active index at x hat, but all I, then we will have that the nf1 normal cone to f1 at x bar is exactly equal to sx bar. This is a very, 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 very fundamental result of convex optimization because it tells you what are the Lagrange multipliers doing. Who are they? They are somebody who generates an element of the normal cone to f1 at x bar in such a way that that element is exactly the negative of the gradient of f at x bar. So that's the key idea. So now let us see how can we show that this is nf1 x bar is equal to sx bar. So what we already know is that sx bar is subset of nf1 x bar. So sx bar, because sx bar is a finitely generated cone and we know that a finitely generated cone is closed, sx bar is a closed convex cone. Now we want to show the reverse step, that nf1 x bar is subset of sx bar. Here again we will use one of the greatest tools a mathematician has in his or her kitty, the method of proof by contradiction. This is the star performer in the world of mathematics, the method of proof by contradiction. Without it, many proofs wouldn't have been simple. I'm not telling that this proof is very, very simple and you can understand in one go. That's not the case. What you really have to first show that, okay, I have to show that the normal cone to f1 at x bar is also contained in sx bar, is a subset of. On the contrary, you will assume that there is a v element of nf1 x bar, but that v is not element of sx bar. So if it is to be a subset, then every v in nf1 x bar must belong to sx bar. So but let there be one v for which this is not true. So if this is the case, then because Sx bar is a closed convex set and V is not element of Sx bar, you can apply the separation theorem that you learned earlier to show that there exists a non-zero vector P in Rn and a beta in R for x which this is true. You can take beta to be 0 also, doesn't matter. So here, since 0 is in NF1 x bar, so this is what you get, that for P of W is less than equal to beta, strictly less than PV. So there is a strict separation because there is a closed set and a point outside it, and the point is V. And W is element of Sx bar. W is element of Sx bar. So NF1 x bar. So sorry, I'm making a mistake here. Okay, there is a small writing mistake. This NF1 x bar we should replace it by Sx bar. So so I'll just tell you the proof. Though I'll send you the error term here is that in this particular proof it should be Sx bar and not this should be not NF1 x bar. Here is a mistake. So I am applying a separation theorem where my Sx bar is the closed set and V, that element of the normal cone, is outside. So that this is satisfied for all W in Sx bar, not NF1 x bar. So this is our writing mistake. So what we essentially show is that for all W in Sx bar, P of W is less than equal to 0. We will show that. Now, since Sx bar is in NF1 x bar, this is not required because this is true for Sx bar. So what does an element of Sx bar look like? Any element of Sx bar would look like this. So there is this part has to be actually changed when I type it. So there is a little mistake, but what I claim that PW is less than equal to 0 for all W element of Sx bar is true, but I had made a mistake in writing NF1 x bar. I apologize. But what happens? So this whole thing is not required actually. This argument is not required. There's a mistake. I think I have not carried over that mistake anywhere else. I guess no. Okay. So we will not get too much into its details. So because the proof is pretty involved, I don't even want you to get so much bogged up with the proof. So the thing is that once you have applied the, say, the power of the separation theorem, once you know that for every W element of Sx bar, this is happening. So you choose any W, any W is of this form. So whatever it's for all lambda greater than 0, I element of Ix bar. Doesn't matter whatever we have lambda I. Which means if this has to happen, none of this grad GIXP is strictly bigger than 0. It cannot happen. If it is so, then I can take a lambda I greater than equal to 0 with this, and all the rest lambda i's are 0, and the whole sum would become strictly greater than 0. So that would be wrong. So this would happen. Here I have written that you take all lambda I equal to 1 for I element to Ix bar and lambda j equal to 0. So if I put 1 here for say lambda 1, I put 1 and put rest of the 0. I'll immediately get grad g1 x bar p is less than equal to 0. So this is true for every I element of Ix bar. So what you want to then construct is a set like this. The idea, of course, it's a kind of, we might say, how do you get the idea of Q? The idea of Q actually comes from actually trying to understand that if I consider, so P belongs to a set where this condition is satisfied. Now I am looking at the interior of the set, because once I come to the interior, the Slater condition type of thing is very well used. Slater condition simply means that my feasible set actually has an interior. Okay. Now what I do, I'm looking at this set Q where I'm looking at this strict inequality, not this kind of inequality, less than equal to type, but strictly less than 0. I will show by Slater condition that this has a element, it is non-empty. So if x hat is the point which satisfies the Slater condition, that is gi x hat is strictly less than 0, then by using convexity, here you can see that I can show that x hat minus x bar is actually satisfying this inequality. So with u equal to x hat minus x bar, that is inside Q. So Q is non-empty. Now I will not get into the detail of the proof. What will show is that Q is an open set. Now if you take the closure of Q, the closure of Q simply becomes this. Because if you take the interior of the, you can actually show that the interior of Q closure is all elements which satisfy this. You can actually show that the interior, because Q is non-empty, this Q bar, this set, which is actually the closure, the Q bar, the interior of Q bar is actually this set. So once you show that, you know that the closure of the interior of a convex set is the closure of the set. But if the set Q bar, for example, so the closure of the interior of Q bar is the closure of Q bar, but Q bar is closed, so it is equal to Q bar, but the interior of Q bar is actually Q. So you have Q and its closure. So your P actually is lying here. What you now show is that you take any x bar, the reference point at which you are computing this normal cone, and then for any lambda strictly greater than 0 and very small, you can actually take a u inside Q and show that x bar plus lambda u is strictly greater than 0 for all I element of I x bar. And hence by continuity of gi, you can actually show that for every gi you can find a lambda sufficiently small for which this is true. And hence showing that gi, when x bar plus lambda u is actually an element of F1. Thus, if you now can write u as F1 minus x bar by 1 minus lambda, it shows u must be in the cone generated by F1 minus x bar. So this must be in a part of a cone. What is a cone generated by a given set? Let A be a given set. What is the cone generated by A? So any element V of the cone generated by A is of the form lambda of A, where A is some element of capital A set. So capital A is the set. So a cone generated by the set A is the set of all elements V, which can be written as lambda of A, where lambda is greater than or equal to 0 and A is any arbitrary element of the set A. Now this F1 is a convex set, which is because feasible set. So F1 minus x bar is also a convex set. So when you generate a cone of a convex set, you get a convex cone. And so here U belongs to this convex cone, because F1 minus x bar, you take and this is some element of this set F1 minus x bar, and so take some element. So U is equal to 1 minus lambda some element of F1 minus x bar, say Z minus x bar. So that actually belongs to the cone generated by F1 minus x bar, which is contained in the closure of the cone generated by F1 minus x bar. So Q is contained in the closure of the cone generated by F1 minus x bar, and Q closure is nothing but the smallest closed set containing the set Q, and so Q closure is a subset of this. What you can show is that if V is in the normal cone, which it was, right? So there was that mistake. So W's were in Sx bar. Please understand, again I want to clarify this mistake here, that here all up to here, this statement is not required. All these statements, this has to be replaced by Sx bar. So I apologize for that. So once we have done what we show, that if V is element of NF1 X bar, then for any gamma which is in the closure of the cone of F1 minus X bar, V gamma is less than equal to 0. But since P is element of Q bar and P is thus in cone of closure of the cone of F1 minus X bar, V gamma is also, when V of P is also less than equal to 0. But this violates the separation condition which show where we had V of P is strictly bigger than beta, and beta itself is greater than equal to 0, so it is strictly greater than 0. So which concludes that NF1 X bar is in Sx bar, and hence NF1 X bar is equal to S of X bar. So in the next thing, once we have finished, we will, in the next and the last class, we'll introduce the Karush-Kuntakar conditions. Thank you very much.